So for problem number 62, it says you could perform a popular trick by dropping a dollar bill lengthwise through the thumb and forefinger of a fellow student. Tell your fellow student to grab the dollar bill as fast as possible. He or she can have the dollar if they're able to catch it. The length of a dollar is about 15.7 centimeters, and the average human reaction time is 0.2 seconds. Is this proposal a good deal? Justify your answer. So we draw a picture of a dollar bill, and we label that it is 15.7 centimeters long, and the human reaction time is 0.2 seconds. So if we look at that and we wanted to, basically what we're trying to do is see if your fingers can pinch close, which should take about 0.2 seconds before the dollar bill falls through the grasp of your fingertips. So essentially what we need to do is figure out how quickly the dollar bill can go through. In other words, can I move 15.7 centimeters in less than 0.2 seconds? So this is not really a difficult problem to do, but what we're trying to do in essence is see, will somebody be able to catch the dollar? My suspicion is that you wouldn't be able to catch the dollar. I don't think that, I think that the dollar bill can move the 15.7 centimeters in less than 0.2 seconds. So this is just a basic free fall question. The object in this case is the dollar bill. The distance that it's going to travel is 15.7 centimeters, and we'll have to convert that to meters in a second. And then the amount of time that we're trying to beat is 0.2 seconds. And so we just need to kind of start going through our picture and labeling things like initial velocity, final velocity, acceleration due to gravity, how much time it is, and all those things, and then pick an equation and plug the stuff into the equation and see what happens. So one thing I know is that the acceleration due to gravity is going to be 9.8, and I guess I'm going to restate the question in my own words. Can an object move 15.7 centimeters in free fall faster than 0.20 seconds? And I really don't have a lot of information, but if we start thinking about it, maybe I can pull some more information. So the acceleration due to gravity is 9.8 meters per second. The kinematic equations for free fall in your book takes everything that has gravity in it and assigns a negative to any term that has g in it. And so our acceleration due to gravity is actually g. So we're going to use the free fall equations, and that automatically is going to consider that we're traveling in the negative direction. Okay, so anytime that you go upwards from the center of the earth, that's a positive direction. Anytime you go down towards the center of the earth, we would consider that a negative direction. However, your textbook in the equations automatically inserts the negative sign, and so we're always going to think of g as equaling 9.8 meters per second. So I have an equation, or no, I'm sorry, I have the acceleration due to gravity, I have the length, and I'm going to look for an equation that will help me do both. So I chose delta y is equal to v naught t minus 1/2 gt squared because I know the initial velocity is going to be 0 meters per second, so the first term kind of cancels out. I'm left with negative 1/2 times g times t squared. Well, 1/2 of 9.8 is going to be negative 4.9. My delta y is in centimeters. In order for everything to work out the way I need it to, I need to convert the 15.7 centimeters to meters. So that would be 0.157 meters. And so I'm going to plug that in for delta y. Then I'm going to solve for t. So I have 0.157 meters. It's negative because the dollar bill is falling down. In other words, the dollar bill is going to move in the negative direction. My equation is going to make 4.9 negative. If I divide both sides by negative 4.9, I'm going to get a number. And then on the right-hand side of the equal sign, I have t squared. So 0.157 divided by 4.9 is 0.38. That's equal to t squared. To undo the square, I take the square root of both sides. Oh, I apologize. It's 0.03. And I hit the wrong button on my calculator. So it's 0.032. Take the square root of both sides. And then I'm going to get 0.1789 seconds. So when you look at that, the amount of time an object can travel, 15.7 centimeters, is 0.1789 seconds, which is slightly less than the 0.2 seconds. So it's not fair. Nobody would ever be able to catch the dollar. Okay, so now for problem 64, it says a boy throws a stone straight up with the initial velocity of 15 meters per second. What is the maximum height the stone will reach before falling back down? So what we want to do is, first step would always be to draw a picture. So we're going to draw a picture of the boy throwing the stone up in the air. We're going to label all the things that we think that we know. And then from there, we are going to try to make some sort of calculation. The question specifically asks, what is the maximum height? So that'll probably be delta y. And so sometimes people make fun of the fact that I always draw stick figures. And so I drew my person who throws a stone straight up in the air with the maximum height. And I, for some reason, forgot to put the letter T on the word height. And we know a couple of things. G, the acceleration due to gravity, is 9.8 meters per second. We know that the velocity, the initial velocity, is 15 meters per second, or 15.0 meters per second. We know that the final velocity, when the stone reaches the maximum height, it's going to be 0, because it'll slow down, slow down, slow down, stop, then reverse direction and come down. So it's at its highest when the velocity is at 0, and then it'll reverse direction and start falling back down towards the ground. So what I want to do is I want to pick an equation that has delta y in it, that has the initial velocity, has the acceleration due to gravity, and then the final velocity as well. So that would be v squared equals v naught squared minus 2 times g times delta y. And now I just go in and plug in all the numbers. I have numbers for everything except for delta y. As I start to solve the equation, 15 squared is 225. I'm going to move the 225 to the other side of the equation by subtracting 225 from both sides. That's equal to 2 times 9.8, which is negative 19.6 times delta y. So, and 0 squared was 0. Last step, I'm going to divide both sides by negative 19.6, and I get 11.47 meters, or 0.48 meters, is equal to delta y. So when I throw a stone up with the initial velocity of 15 meters per second,